Electric flux, it is defined as the number of electric field lines crossing the unit area normally. Let's consider this is any surface. You know, area is a vector quantity and area vector is always represented as normal to the surface. Let this is the area vector A. If the electric field lines are crossing this surface, let's say this is the direction of electric field and is crossing this surface. This is the way field lines are crossing this surface. You can see angle between area vector and electric field is theta. Electric flux as it is defined as the number of electric field lines crossing the unit area normally. To the surface area normally means in the direction of electric field. In the direction of area vector. So here, what is the value of electric field in the direction of area vector? So that is component of electric field. So flux phi you can write as component of electric field in the direction of area vector is E cos theta into A. So this all you can also write as E dot A. E dot B is AB cos theta. Here E dot A, that is EA cos theta. So equation for electric flux phi is E dot A, that is EA cos theta. Flux is maximum when value of cosine function is maximum and cosine function value is maximum and theta is equal to 0 degree. If theta is 0 degree, cos 0 value is 1, so flux is maximum positive. If theta is 90 degree, cos 90 value is 0, flux is 0. And if theta is 180 degree, cos 180 minus 1, so flux is maximum but negative. Now here, theta is the angle between area vector and magnetic field. Area vector. First of all, area is a vector quantity. Now what is about the direction of area vector? Direction of area vector. Say, if it is a single surface, let's say this is the surface. The area vector for this surface, it is always normal to the surface. Normal to the surface means it can be outside also, it can be inside also, means outward or inward. Normal to the surface, outward, normal to the surface, inward. It can be in any direction. One thing is that when in any problem for this single surface, when you consider the area vector in a particular direction, whether it is outward or inward, then throughout the problem you have to consider the same direction. If it is closed surface, it can be of irregular shape, it can be a regular spherical surface or square, this cube, cuboid, parallelepiped, whatever it is. For this kind of closed surface, area vector is always outward. To the surface element, area vector is always outward. Any surface element if you take, area vector is always outward. For this all faces, area vector direction that is outward. Different face to the surface, perpendicular it and outward. So remember always, for any closed surface, area vector is always perpendicular to the plane and outward. For a single surface, it can be outward or inward. Okay. But throughout the problem, the direction you have to consider same. So this way, if you decide the direction of area vector, then if you compare it with the direction of electric field, then you can see whether the angle is less than 90 degree or greater than 90 degree. Accordingly, the value of flux can be positive or negative. Next is Gauss law. Gauss law, what it says that suppose any charge, if it is enclosed by a Gaussian surface is the imaginary surface drawn around the charge. It is not necessary that that surface which is drawn can be always of regular shape. It can be regular or irregular. Whatever the shape of that condition, that is, it should enclose the charge. If the Gaussian surface is enclosing the charge, the net flux through this surface, you know that electrical lines from this charge are ideally outward, they are crossing this surface, so the flux through this surface is, according to Gauss theorem, flux phi is 1 by epsilon 0 times charge enclosed by the surface. So we can write the Q inside the surface, you can write as phi is equal to Q in by epsilon 0. This is what the statement of Gauss theorem. Now, how this statement comes? Let us see. If we consider, suppose, a charge Q and the Gaussian surface which we consider that is, let's say, of regular shape of radius r. If the radius of Gaussian surface is r, then we can say due to this charge Q at a distance r, electric field value will be kq by r square, where k is 1 upon 4 by epsilon naught q by r square. For this Gaussian surface, area of Gaussian surface is 4 pi r square. So, if you find the flux, as flux phi is E dot A. Now here, due to this charge, as area vector is outward, electric field is also outward. So angle between E and A is 0 degree, and that's why flux is E dot A, that is equal to E into A. Here, this whole surface, if you take small element of the surface as dA, then you can write this as E dot dA integration closed surface. Electric field is constant integration of dA over closed surface, that will give you total surface area A. If you put the values 1 upon 4 by epsilon naught q by r square into 4 pi r square, 4 pi r square, 4 pi r square, that will cancel. What is left? That is q by epsilon naught. So this way you can prove the Gauss theorem. Okay. This is a regular surface. Similarly, for irregular surface also you can prove it. Okay. The proof that is not in the syllabus, just for your knowledge. Applications of Gauss theorem. First application is to find electric field due to straight, infinitely large charge conductor having uniform linear charge density lambda. Infinitely large straight conductor. Let us consider this conductor is of infinitely large. Infinitely large meaning that doesn't always means that it has no end. But for example, suppose due to this conductor, if you want to find electric field at a distance equal to 10 centimeter, in that case, if the length of the conductor, if it is say suppose 3 meter or 5 meter, with respect to that unit meter, centimeter is very small, then you can consider it as an infinitely large. So here, this is a conductor on which, let's say, certain charge, positive charge, say Q, it is distributed. The length of this conductor, this portion, let's say it is equal to L. Then charge Q, it is distributed over this length L linearly. So the quantity Q by L represented by symbol lambda, that is called as linear charge density. SI unit will be coulomb per meter, because it is a charge per unit length. Let's say this linear charge density, it is uniform. For this conductor, if you want to find electric field at a distance, say r from this conductor, what you need to do, that is you have to enclose this charge through a surface, and that is what we call as Gaussian surface. It is an imaginary surface. So what is the shape of that imaginary surface? If we consider uniform shaped surface, then it is, we can say, this type of infinitely large cylinder of radius, let's say it is r. If this radius is r, distance is r, then the radius is also r, length of the cylinder is L. If it is infinitely large, then accordingly, whatever is the length of the conductor, accordingly the length of the Gaussian surface you can consider. Now electric field due to this charge is always radially outward, so this is the direction of electric field. For this Gaussian surface, area vector is also outward. Area element latitude is dA, then electric field and area element both are in outward direction. And that's why the angle between them is 0. So far, due to this small surface, flux due to this small surface, if you write as d phi, that is equal to E dot dA. Both are in the same direction, that is why it is E into dA. If you want to find the flux due to the whole surface, then flux phi is equal to integration of d phi. Okay. When you integrate electric field on this Gaussian surface, that is curved surface, all points are at equal distance from this charge. So electric field that will be same for this curved surface. Area value will be 2 pi r into L. You consider only curved surface, not this cylindrical surface, because electric field is radially outward. So to this circular surface, electric field is parallel to the surface. So area vector and electric field angle between them is 90 degree. So for these two surfaces, flux will be 0. So flux is only due to this curved surface. And that's why one equation of flux, you can write that flux phi is equal to E into 2 pi RL from the definition of flux. According to Gauss theorem, this charge is enclosed by the Gaussian surface, therefore flux phi is equal to, you can also write as Q by epsilon 0. So equating these two equations of flux from equation 1 and 2, you can write as E into 2 pi RL, that is equal to Q by epsilon 0, and therefore E is equal to Q upon 2 pi epsilon naught R into L. Therefore, you can also write this as Q by L is a linear charge density lambda. So you can also write lambda upon 2 pi epsilon naught R. This value, if you multiply and divide by 2, denominator you will get 4 pi epsilon 0. So 2 in numerator, lambda upon 4 pi epsilon naught R. This quantity 1 upon 4 pi epsilon 0 is represented by symbol K. So the value of electric field will be 2K lambda by R. So you can say electric field is inversely proportional to R if charge density is uniform. So this is the equation for electric field due to linear charge distributed over infinitely long wire. Another application of Gauss theorem is to find electric field due to infinitely large plane charge sheet. Let us consider on this surface, infinitely large it is, certain charge, it is distributed uniformly. Here charge Q, if it is distributed on surface area A, then this quantity is represented by symbol sigma. Sigma is equal to Q by A, that is called as surface charge density. SI unit is coulomb per meter square. Let this surface charge density is uniform. To find the electric field due to this charge sheet at a certain distance from this sheet, so we need to draw the Gaussian surface which can enclose this charge. Now if it is an infinitely large sheet, then to enclose this charge sheet, we need to draw the Gaussian surface, that also on both sides you can draw the infinitely large sheets. Okay. Then, so this is the infinitely large Gaussian surface on both sides. If you consider like that, if you can enclose this charge, then let us consider certain part of this surface, let's say surface area A, on which charge is Q, surface area is A. Then accordingly Gaussian surface also Here it is area A. Here also Gaussian surface area is A. So for this imaginary cylinder, the electric field lines due to this charge sheet, let you consider the charge sheet in this vertical plane, electric field is outward. For this area vector also electric field is area vector is outward. So electric field and area vector directions are same. Electric field and area vector both are in the same direction. So flux due to this, you can write as flux phi is equal to integration closed surface E dot A. Here is the electric field, Gaussian surface area, Gaussian surface, this as well as this. So there is total Gaussian surface area is 2 times A. This is one equation. Another, according to Gauss theorem, flux phi is equal to Q by epsilon 0, because charge Q is enclosed by the Gaussian surface. So phi is equal to Q by epsilon 0 from equation 1 and 2. You can write E into twice Q, that is equal to Q by epsilon 0. Therefore E is equal to Q upon 2 epsilon 0 A. Q by A is represented by symbol sigma, that's why E is sigma upon 2 epsilon 0. So this is the equation of electric field. See here, sigma is constant, 2 constant, epsilon not constant, so everything is constant quantity. So you can say that electric field due to charge sheet is uniform. It is independent of distance. Okay. So this way you can find electric field due to plane charge sheet. Third application is to find electric field due to spherical charge shell. Spherical charge shell. Let us consider the spherical charge shell. Charge shell is a hollow sphere. So here charge shell means on this hollow sphere, let's take charge Q, it is distributed uniformly. Charge Q is distributed on this hollow sphere of radius r. Then let's say represented with symbol capital R. Then surface charge density sigma is equal to charge upon area. Surface area sphere is shell is 4 pi r square. SI unit is Coulomb per meter square. It is surface charge density. Now to find electric field either inside the shell or on the shell or outside the shell, let us consider different case. One is inside the shell. Inside the shell means at a distance r which is less than the radius of shell. Let's say if you want to find electric field at this point which is at a distance r from this shell, the center of the shell, then Gaussian surface if you draw, this is the Gaussian surface. What is the charge enclosed by the Gaussian surface? Charge is outside the shell. Charge is outside this Gaussian surface. On the shell, Gaussian surface is inside. So charge enclosed by this Gaussian surface is 0. So we can say, according to definition of flux, phi is equal to E into 4 pi r square. Electric field that it is E, surface area of Gaussian surface is 4 pi r square. But according to Gauss theorem, flux phi will be equal to 0 because charge enclosed by the Gaussian surface is 0. And that's why from these two equations we can write from 1 into E into 4 pi r square is 0, and therefore E inside the conductor is 0. Inside the shell, electric field is 0. Another point, if we consider the point outside the shell. Let's say this point is outside the shell. Radius of that is r, and the Gaussian surface which you draw, this Gaussian surface is enclosing this charge. So here, if the point is outside the shell, so the condition that is r is greater than r. So in that case, according to definition of flux, E into 4 pi r square, that is the flux, and according to Gauss theorem, flux phi is Q by epsilon 0. So equating these two, you can write E into 4 pi r square is equal to Q by epsilon 0, and therefore E is equal to Q upon 4 pi epsilon 0 r square. See, 1 upon 4 pi epsilon 0 is represented by simple k, so this is similar to electric field due to a point charge. So if you want to find the electric field outside the shell, you can consider the shell as a point charge. Okay. This equation also you can write as, from this equation you can write as Q is equal to sigma into 4 pi r square, and therefore electric field you can write as Q is equal to sigma into 4 pi capital R square, on this is 4 pi epsilon not r square. So electric field equation will be E is equal to sigma by epsilon 0 capital R by small r square. Sigma is constant, epsilon 0 constant, capital R constant, so you can write E is inversely proportional to r square. So here electric field due to this charged shell outside it is inversely proportional to r square. If you consider the point on the shell, it means r is equal to capital R. In this equation, if you put the value capital R is equal to small r, then E is equal to sigma by epsilon 0. So on the shell, electric field is sigma by epsilon 0. So all these values if you write and represent the graphical variation of electric field with respect to distance, then for the shell at a distance r is equal to capital R, electric field is sigma by epsilon 0. Outside it is inversely proportional to r square, inside it is 0. So graphical representation of electric field, this way it varies. So from the graph you can see inside the shell electric field is 0. On the surface it is sigma by epsilon 0. Outside it is inversely proportional to r square. So this way variation of electric field due to charged shell can be represented.